All right, welcome. This is the May ML Papers Talk. So we've got two for you. Today, I'm going to start us off by talking about how to deal with long context. So a few months ago, talked about streaming LLM. So this was the attention sinks paper where they said, hey, when you just kind of like do a window when you get past the context length that your model was trained on. So if your model was trained on 4,000, by the time you get to 4,001, suddenly model performance crashes. And what they discovered was that the models are paying attention to the first token, the first few tokens very heavily. And so there's a fix for that. But ultimately, what people want is to train models on longer context. But regular vanilla transformers, they have a quadratic cost. And so if you had a model that was length 1,000 and now you want a model with length 1,000,000, then training those million, because it's 1,000 times longer, is going to basically be ballpark 1,000,000 times more expensive for each batch that you train compared to the length 1,000. So that's something that just doesn't really scale well. There's a gazillion papers out. This is a fairly recent paper. It's interesting. And so this one is titled Leave No Context Behind, Efficient Infinite Context Transformers with what they dub Infini-attention. I think the infinite is a bit of an exaggeration, but it does scale a lot better than just vanilla attention. So that's the problem. And one of the questions is this the technology that's being used in the latest Gemini models by Google? Since they do claim they support whatever, million and a half token lengths. Okay. So there are some themes that'll be similar if you're looking at other papers that are addressing this same problem. So this paper seems to combine three concepts. There's an old paper called Transformer XL, and we'll go into the details, but basically the general gist is it divides up your text into two segments. And so a regular window would just say, okay, my window size is whatever, 128. I'm just going to look at the most recent 128 tokens, and it's going to slide that window every time you move one token over. What this does is it basically uses two windows, and the old one is sort of meant to be sort of like this rolling history that kind of like keeps things coming. We'll get into the details. There's also a fast wait memory paper. The primary author on this paper, he was one of the authors on this fast wait memory paper. And so what this is about, we'll talk about, is basically having a pretty fast technique which is designed for you to be able to store values in there. And ideally, if you have sort of similar keys and similar values, then even if you try to pull something out, you'll sort of get this nice interpolated result, which means that there's not a hard limit. Like if you just build like a regular hashing table kind of a memory, then if you get something that's a hash miss, then basically you just get nothing. Okay, so in this case, it's more of like an associative, a similarity-based memory, and you can pull things out. And the third thing that they pull out is there was this linear attention, linear transformer paper, which instead of doing quadratic attention, they did an approximation, and this model had linear cost, but the performance wasn't as good. So the problem with each of these three ideas is they've tried to build some kind of sequence model using just these technologies. And at the end of the day, once you scale big, they just don't work as well as transformers. So in this paper, we kind of have a blend of all three of these technologies. And my personal opinion is it's not going to be infinite. You're not going to be able to go, but if in all practical purposes, it lets us go to context lengths that are, say, 1,000 times longer than previous, maybe that's good enough. Maybe if we have 32,000 models and we can get to 32 million, then for 99.9% of people, even if you want to like stick a book in there, 32 million tokens is enough that like you have most of the context you want for whatever your question is. All right. And so what we'll see then is that the memory cost is basically constant. It's just defined by how big you define this fast wait memory to be. And then the processing cost is linear with the number of chunks, linear in the length. So that's basically what people want, is they want something that scales linear. So we'll start by talking about Transformer XL. All right. And so we've got two diagrams here. On the left is standard attention. Okay. Every query and every key get compared to each other. Yes, question. Okay. And all of this is just the overview. I'm actually going to explain all of these points in the rest of the. No, that's cool. But if there's something that I don't cover, please ask a question. So, so the diagram on the left, this is regular attention. And so the idea is if the current token is sort of the dark blue squares, okay, then you can see that every query in the dark blue square is going to look at every key to its left. So as you get longer and longer, by the time you get to like 1,000,000, I'm going to be comparing my query to 1,000,000 keys. That's just the way it works, okay? So you can reduce this cost by doing window detention, which is the diagram on the right. So this has a window size of 4, obviously a real LLM. We're going to use a number bigger than 4, but for the purposes of just diagramming it, you can see you've capped your cost. I'm only going to look at 4 keys. In this case, you can see I'm going to look at the key for myself. Do I want to attend to myself, or do I want to attend to the 3 previous things? All right. So you can decide whatever window size you want, but that's going to cap your cost. The problem with this window view isn't the performance of it. I'm sorry. Yeah. In terms of speed, the problem is the performance of it in terms of how well does this work as a language model. So in this case, it's a hard cutoff. So if you mentioned something 1,005 tokens ago, you said the main character's name is Bob, and then you had 1,000 tokens talking about something else, and now you're like talking about the main character again, you use this window and it has no idea who Bob is, right? So all of these different techniques want to do something where they say, is there a way we can remember that Bob was mentioned, but not pay that full cost of having to attend to every single token to our left, right? So Transformer XL had this idea that basically we're going to use these 2 segments that I mentioned. So you can see the regular window, again, is still this like light blue area, okay? But we're going to have this green area, which is this other special segment. Now, when I was going over the paper last night, I'm like, well, in some ways you could say, isn't this just a window of 8 instead of a window of 4? And the reason why it's not just a bigger window is because they actually have different parameters, different weights for the green part than they do for the blue part. Okay. And so my understanding is the desire is that you want the model to learn to do something different with the green tokens. What you want it to do is sort of, in a perfect world, just accumulating important things from the past. Whereas for the blue area, you're just doing regular attention and you're just saying, should I attend to have the word he? Who is he? Oh, look, 8 words ago was Bob. And so I'm going to tend to Bob. Okay. And so that's the general gist of this. So a little bit more detail. Basically, if you're we're calling these now segments instead of windows, if you look at the paper. If the segment size is S, then your queries are really only looking at S keys. Okay. But for the green part, there's this other thing that happens. And so you really have double that. You have 2S for your keys and for your values. And again, this is how it manages to try to learn something different for the green part than for the blue part. If you just had the same weights on everything, then it really would just break down into a size 8 window and it wouldn't be any better than regular window detention. There's some more technicalities I'm skipping just in terms of like how they were using relative position embeddings instead of absolute position embeddings and things like that, just to ultimately make it work, but not really trying to go into all the gory details for this model. So a couple diagrams here. Here, if you look, there's the segment on the right. This is our segment of size 4. That's our current segment. And this area in the dotted box is the previous segment that I was showing in green before. And so what this diagram is just showing is that normal attention would just have the gray weights that let you look at things. So token 12 here on the far right would be able to see itself in the 3 previous tokens. But actually, there are these green weights that basically allow you to see information from further back. Okay. And the idea is that, well, hold on a second. If in a certain layer, the very first layer, I see an extra 4 back, and I bake that information into my outputs, then that means that my outputs are really like looking at A, and somebody else that's looking at me can benefit from the fact that I'm looking further back. So the next diagram just kind of shows this idea that if you imagine this, what is this, layer 1, 2, 3, 4, this fourth layer, it maybe can only see 4 tokens back directly, but that token has information from 4 tokens back, and then that token has information from 4 tokens back. And so the idea is that as you move up the layers in this model, your window of information that you can be collecting grows. So if you're familiar with CNNs and the idea of receptive field, if you only have 3 by 3 features in your CNN, the very first layer only has a receptive field that's 3 wide. But the second layer is going to be 5 wide, and then the next layer will be 7 wide, because you're only looking at 3 things, but each of those has its own, receptive field. So that's the general gist here behind Transformer XL. And I mean, it worked better than window attention, but it was clearly not the solution. So let's take that concept and let's do a little spin on it. Let's actually make it a little bit better. So what Infini-attention does is, I'm gonna keep this first bullet on here for reference, okay? Transformer XL, we're actually processing 2 segments. But what we're gonna do is, instead of having that green segment that we're processing, that we have some weights, that we hope it learns to accumulate information, why hope that it learns to accumulate information? Let's just explicitly put a memory device there whose job is to accumulate information. That's the idea in this paper, okay? So if this is now a memory, then we don't have to say, oh, I hope you learned some weights, some whatever. It's like, no, I'm just going to implement a write operation. I'm going to implement a read operation from this memory. That's the gist of this. So let's talk a little bit about how we do sort of this memory. I'm not going to go into all the math, all the details, but this next slide is the mathiest slide in this presentation, okay? So just by background, if you start with a matrix M and its dimensions are whatever the length of your keys are and whatever the length of your values are, okay? Usually they're the same, so this can be a square matrix, but hypothetically all this works even if it's rectangular. And this matrix is all zeros. So this is my memory, it's initialized, it's all zeros, okay? If I take the outer product of my key and my vector. So the inner product would result in a scalar, okay? If I take the outer product, I'm going to get a rank 1 matrix. So in this case, we have row vectors, so it's K transpose V in the paper. So what happens if we take our query and we multiply it by this quantity, okay? So by associativity, query times K transpose V is the same thing if I move the parentheses as query times key times value, okay? And so what this ends up being then is the dot product of query and key times the value. If you recall, one of the places where we've seen the dot product of query times key is in attention, and then ultimately those attention scores that are normalized to 1 get multiplied by the value. So if you've seen the full attention written out, if you see just the attention part, it's queries times keys, and then there's a denominator that normalizes it, so square root of D thing, okay? But if you see the full thing, that's then multiplied by value. So this is basically a mini attention calculation right here just by using a matrix. So what we're going to take advantage of the fact is that in this matrix, we can just keep adding rank 1 matrices and piling them in. And in terms of like linear algebra, if they're all like not like multicollinear, then you can pile D of them in there and you can have perfect recall on everything that you've ever put in there. But if you take advantage of the fact that like, well, some of my queries may be very similar, then what you're going to end up is hopefully just being able to pull out values that are very similar to those two. So you're not going to get, like I said, if you just created a hash table, when you have a miss, you have a hard miss. In this case, what you're going to do is you're going to sort of get the similarity between the keys that are the closest to your match, and that's the values that you're going to pull out. The other thing that's important to note is that if the query and the key don't match in a high dimensional space, the dot product is going to be close to 0. So if you have 500 keys that you've plopped in there, if 499 of them are very different from whatever your current query is, even though you've added all of those to your memory M, almost nothing is going to come out when you multiply it by your query. So this is a slight oversimplification, but basically the idea here is that this mechanism allows us to have a query and associatively pull out the values associated with keys that really match well with my query. All right. So at the end of the day, what we do is when you want to do a write, you calculate your outer product of your keys and your values, and you just sum that into your matrix M. When you want to do a read, you left multiply by your row vector Q, and out pops out is basically this blended value. And again, if only one key exactly matched, you're pretty much just directly pulling that value out. If multiple of them match, then you get like a little bit of a blend, which in fact is actually how attention works, because attention, you don't just attend to one thing, you actually have attention scores that add up to 1, and you're actually blending all the values that come from those locations. So in that sense, it is a similar thing. All right, there's some extra details in the paper that I've sort of skipped here. If you think about it, if you multiply keys and values, and those are not length 1 vectors, then you're going to get something bigger, like the numbers are going to get larger. So there's this sigma function which normalizes them basically because you want unit vectors so that the sizes of your things don't grow when you put it in your memory. There's also this thing that I showed you just in terms of vectors, okay? But the reality is you can do this if you have a length 1000 sequence. You can do this operation on all 1000 of them simultaneously. So you can do this with matrices, and then it's going to run a lot faster on your GPU, but it doesn't change the underlying math, which is why I just like covered the simple case where you're just using vectors, okay? And then there is this other part that was kind of interesting, but for time, I skipped it, where basically what you can do is you can check to see if you think the value is already in there. And if the value is already in your memory, then you don't really need to do a hard write to your memory. And so they have this delta method they do where they basically check first to see if it's in there. And the higher score you get, the closer to 1 you get, the more you downweight the write that you're doing. Okay. So this means that if you have a particular key that appears over and over again, so if like every 5th word is just Bob, 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 over and over and over again, you don't want the whole memory to get overwhelmed by this. And so basically what it's going to say is the more Bob is like firmly written to my memory, instead of just adding that over and over again to the matrix, it's going to downweight so that soon I'm multiplying by 0.0001 before I add it. And so then it's going to kind of quiet that down. So what you want is you want to have like whatever the D most recent keys. You don't want one key in there dominating everything and the other 400 keys to be, like sort of watered down because Bob just appeared so many times. And so you'll see when we see the results that there's this delta method, and that's why I wanted to mention that. All right, let me just pause here. Any questions about either just the idea of we're gonna have these 2 windows, or I know I haven't really gone into all the details of the math, but this is hopefully giving you just a sense for how you can use outer products so that you can use a matrix as a memory device.
Yeah, so for the memory, seems like a more creative way to like link distant data points from each other. Uh, did they go so far as to like, because I'm thinking like human memory, you know, you could have like your first memory as a human being, and then later on you're like at some interview or something, and like out of nowhere that memory gets sparked, and then like now it's got you thinking a whole new thought or whatever. Do they kind of like implement that sort of idea where it's like if they see there's a distant data point with a strong correlation, do they just kind of like save that somewhere in the memory and just like keep it there for like quick for reference? Or is it just more like you're still linking all these distant data points? You're just kind of like narrowing the window so that way you can like save memory costs by prioritizing more recent memories over distant memories. And like, well, I guess what I'm trying to say is like if there's a data point all the way at the first I guess space in the matrix, and then there's a data point always at the last space. Will that window be able to easily recall that first data point if it's important enough, or is it just gonna get lost because they're more focusing more on like recency versus like just hard. I guess before it's just like you kind of link everything together, and that's why it's so computationally costly because you got to go through each point. Like, if that makes sense.
Yeah. So I'm not going to be able to recreate that completely for everyone online, but I think the key part of your question is how do you deal with like more recent things that you've put in your memory versus things that you put in the memory longer ago? Okay.
Yeah.
And the idea here is that if you have these rank one matrices and you sum them, the way it works in linear algebra is the oldest one and the newest one, there is no difference. Until you get interference between them, they all just pile on and they're all perfectly retrievable. Okay. So if you had 500 orthogonal keys and you put them in there, you would get like with no round, maybe like floating point rounding error, but you would get no error. You get perfect recall of all 500 values exactly. Okay. Now, in this case, we have this concept of queries. We have this concept of keys. We're not necessarily expecting that our keys are somehow perfect, that our queries are somehow perfect. But the idea is that this memory, you're just doing a multiply and it is going to extract out based on how well it matched your keys. And it doesn't matter if the keys are more recent or older. Linear From the linear algebra perspective, the matrix is just the sum of these different rank one matrices.
Okay, so then like when you're multiplying the window to the matrix containing all your data points, you're doing because the way I was understanding it is like you're taking that window is just going to be like a smaller matrix, and then you're just kind of like, um, well, I guess what you're trying to say is
Yeah.
you're taking that window and you're applying it to all the data points, and then whatever values you get out, that's going to be determined like how important those data points are.
Yeah, how they do it in the model is a little bit different than how I'm describing it because they parallelize things a little more and stuff like that, right? But there's a slide coming up where I think it'll help a little bit, but mental model wise, just imagine going one token at a time. And so I've processed the first token, and I'm just going to take the key from that token, and I'm going to use that to write to my memory. And then I'm going to process the second token, and I'm going to use that to add to my memory. And then the third and the fourth. Now, obviously, if my memory is thousand dimensional, I'm not going to be able to store a million discrete different keys in there. But the reality is a lot of those keys will be repeated. So you don't actually need a million distinct things. And then how well the memory works is really based on like, hey, maybe if you have like great and excellent and they're very similar keys, then maybe they have very similar values in the first place. So they don't really need discrete memory locations in our memory. So something kind of along those lines. All right. If I still haven't answered your question after I get through the Infini-attention, please bring it up at the end. Okay. So uh, so what we're going to do is, again, Transformer XL, we processed two segments. We're replacing the previous segment with this linearized attention using our memory mechanism, which was on the last slide. This is very inexpensive. We're just doing one matrix multiply. I'm taking my Q and I'm multiplying it by the memory, and that pulls stuff out. So when we're processing text, this is the loop. So I have a diagram on the next slide, and then hopefully also this loop helps answer your question, okay? So we run regular attention with our queries, keys, and values, our QKV attention on the current segment. We then do a retrieve operation from our memory using our query and say, hey, from everything that's in your memory, like what's the best match for the current token that I'm on for my current query, okay? And we're going to sum those two things together. So if my segment size, my window size is 1,000, I'm going to have 1,000 that I'm going to do regular attention on, and I'm going to have this length 1,000 thing coming back from the memory, and I just, maybe I weight 1.8 and I weight the other 0.2, and I just sum them together. Okay. So then this result is the output from our new Infini-attention layer. Okay. But we're also going to say, hey, at this point, I've only done a read. I haven't done a write. So what I need to now do is I need to take those keys and I need to take the keys that we have and I'm going to store them back in my memory for future use when we get to the next segment. Okay. Excuse me. Once I've written all the keys, now my memory is enhanced with all the latest keys. And now what I can do is I can use this updated memory with the next segment of text as I process it. So here's the diagram from the paper. Okay, so the idea is, again, let's say our segment size is 1,000. So we're currently on token, whatever, 9,000. Okay, so tokens 8,000 through 9,000, we're just going to do regular attention. And most of the time, you're going to tend to words that are like in the last sentence or two. So like this is perfectly good for 90+% of the time, whatever. Bob, threw the toy for his dog, and then you say he. What is that referring to? Well, that's referring to Bob, who was the subject of the previous sentence. It's not that far back, okay? But what if you're reading a Wikipedia article and it mentions something in section 1 and it doesn't use that word at all again? And here we are now in section 6, and all of a sudden it mentions this word that was mentioned 5,000 tokens ago. Okay. What we're hoping is that then the keys and values associated with that word have been successfully stored in our memory. And so what we're going to do is when we see that, we're going to have, again, the queries are going to go against the keys in the last 1,000 tokens, and they're also going to just pull from memory and say, do you have a match? Do you have a match for this term that I just saw, but it's not in my 1,000? So the thing that's not clear how it works is then this business of weighting the two, blending the two of them together. So what they do is they have a learn parameter. They call the parameter in the paper beta. Okay, and every single attention head gets its own distinct value of beta. So that means that some attention heads might have a beta that says mostly just use local attention and don't weight the other thing. And some could do the opposite. They could say, just go look back in memory and see if you find something. And then you can have other ones that do blending. So this is a diagram that kind of shows a little bit diagrammatically how you're going to do these two segments at a time. And so to kind of like bring this back high level, okay, so once again, Transformer XL, it processed two segments, but the old segment was just sort of processed in more or less a vanilla transformer attention way. And we're going to replace that with the memory mechanism that we've built. So there are two key distinctions that we get from replacing that. So one is that our memory directly stores values, right? The whole point of attention is you do this whole dot product and all that stuff, but the point of it is to output values. That's what it does. The attention scores are thrown away. They are used in order to pick what values you want, but they are thrown away. The goal of attention is to output values. So in this case, our memory is directly outputting values. So this is much more direct than like hoping that the green weights will learn something and figure out a way to do something. It's like, no, I just ask the memory to give me values back. And then the second thing is that there's this idea that in Transformer XL, as you moved up in the layers, the receptive field grew. Here, you don't have to weight even in the very, very first layer, by the time you're on the millionth token, if that memory works really well, it can recall anything from the previous 900,000 tokens. And so those are the two like big advantages over potentially a model like Transformer XL. So the gist is, if you pick a reasonably big segment size, then you can do local attention that's going to work most of the time on words that are, in the last, I mean, thousands even pretty generous, but like, you're usually attending to things in the same sentence, the previous sentence, the same paragraph. It's just not that often that you have to attend to something, from thousands upon thousands of tokens ago. If your memory works well, and this is probably the biggest if your memory worked super, super duper well, and if it was basically like a mind reader, okay, and if it said, "Oh, you're on token 900,000," the key that you would have wanted to attend to if we did regular attention was key number 137. Let me just give you that one. If the memory can do that, then basically you will see no performance gap with full attention, okay? But that's the really big if, is does the memory remember that well? And also, is it giving you the one that you would have wanted anyway? Maybe it's not giving you exactly the right thing. So those are the things that need to be kind of proved. We one more diagram here. This is the receptive field thing. So on the bottom, Transformer XL in gray, you can sort of see as you move up, the idea is that it can kind of see more, and then everything's gray here because Infini-attention can immediately see everything that ever came before it. Again, assuming the memory works, right? So one more slide here. I talked about this beta parameter, and what the authors say is, hey, if you look, there's actually a whole bunch of betas that are close to 1. So it's basically saying, just do local attention. Just focus on the nearby tokens. There's a lot of parameters, betas, that are close to 0 that are saying, just do some kind of history maintenance function. Don't worry about the most recent 1,000 characters. But obviously, somewhere you have to blend the two. And so it looks like what's happening is, I don't know if I completely buy this argument, but according to the authors, there's specialization. And so then there's going to be a different sort of learned pattern for what to do with the old stuff and what to do when you're blending stuff. The recent stuff, it might work the same way as just a regular model because it is just doing attention on the most recent tokens. All right, so I think, yes. So now I've got like 3 or 4 slides on results. The first thing that they showed is their perplexity is a little bit lower. So perplexity is how well can you predict text that's in your test set? And obviously, the better you understand the context of what somebody's talking about, the better a job you can do predicting the next word. It's a little bit better. I don't find this the most compelling result. This is a little bit more interesting. So there's this passkey task, okay, where you basically have some string, and what you do is you just hide it in a really long string. So, you're like, apple, banana, guitar, violin, apple, banana, guitar, violin, apple, banana, guitar, violin, apple, banana. You say this like 50,000 times, and then you're like, hey, the passkey is 1, 2, 3, 4, 5, 6. Remember this. Apple, banana, violin, guitar, apple, banana, violin, guitar. And then you get to the very end of 1,000,000 tokens, and you're like, hey, what was that passkey I told you? So this is kind of a challenging task for current LLMs. Sometimes even when they have a big enough context, they don't necessarily pay attention to the right thing. And so to do this right, what you do is sometimes you hide the passkey near the beginning, sometimes you hide it near the middle, and sometimes you hide it near the end. So if you only did one of those 3, the model could kind of cheat a little bit, okay? But if you do all 3, then that means the model has to actually have attention that somehow works, whether it's anywhere in the tokens. And so in this case, the model 0-shot vanilla does not do very well. But then when they do a little bit of fine tuning on this task, you can see they get close to 100% performance on this. And then I don't know where top, yeah. So 32,000, 128,000, 250, So they're doing really, really well, up to 250,000 tokens. Still good, 512. And then it's not, not 100%, but you can see it's like 96% accuracy, 95% accuracy on 1 million tokens. So this is better performance than a lot of models. I'm not sure if the passkey task would be a little harder if you didn't repeat the nonsense. So if you use just kind of like random text with a large variety of words in the padding, instead of just doing like apple, banana, guitar, violin over and over again, if you really like mix things up. I think for the reproducibility, that's why they use this, because then they can say everybody used the exact same text. But if you had more like random text, it would be a little bit harder to enforce. When you did length 100,000, did you use the exact same kind of nonsense words as somebody else? But it is possible the model can cheat a little bit to basically just say, I'm going to ignore the word apple, and I'm going to ignore the word banana, and I'm going to ignore the word guitar. So it's not 100% certain just from this one downstream task is the model really doing, but it seems promising. They did some book summarization, so you have these 500,000 token book excerpts, and they're mostly comparing this against like BERT type encoder models, and they did pretty well. This seems like a reasonably hard task, but Rouge is not a great metric, so I'm still not 100% sure how strong this result is. And then finally, just they say, hey, and when we did this, let's try this on different length books. And what you can see is that as the input text got longer, their performance got better. And so I don't think this is like super strong in and of itself, but it is informative to basically say, if it weren't for this, maybe their Rouge scores were high just because they were good at summarization, and it had nothing to do with the Infini-attention thing. Like you just happen to build a model that's good at summarization. No, what they're saying is summarization gets better the more text you give me, and that's the pattern you want to see. You want to see that like it actually is looking at all of that. So when you give me 100,000 instead of 30,000, I made good use of it, and my performance improved. So so overall it seems promising, and of course now in the last year or so since ChatGPT, everybody's trying to make money, and so then these papers don't really go and expose as much information as they used to. So we don't know at this point whether or not Gemini is using this Infini-attention or it's using some other trick or what. At some point it'll leak, but hopefully for the Gemini people, it'll leak after a year. Metric for what? Sorry. So the Rouge question is what the Rouge score measures. Rouge is basically like, here is our official summary answer, and I'm going to check to see whether you have a lot of words in common with it. Okay, and so we can do unigrams, and then like you can do versions of Rouge where you check bigrams and trigrams and other things, and you kind of blend those together. Yeah, it's accuracy. Right, but it's accuracy based on the ground truth summary that somebody wrote. And so you could imagine that like if your model output excellent, but in my ground truth I had the word great, you don't get any Rouge points for that. You need exact word matches. So that's why I'm saying Rouge isn't a great thing, but nevertheless, all models have the same handicap that they don't get points unless they have exact word matches and exact bigram matches and blah blah blah. So it's better than nothing. But yes, that's why anything you see that uses Rouge, like blue scores, Rouge scores, take it with a grain of salt, because we know that they're not perfect metrics. All right. So just to wrap up again, let me just check real quick, chat. Oh, okay, yeah. So going back, can I go back? Any of these slides where you see linear, linear, delta. So again, linear was this memory that I was talking about, the basic technique they used. And delta is where they said, we're going to do this trick to check to see if the key's already in my memory. And if it's already in my memory, I'm going to downweight it. And so generally speaking, what they found was that the plus delta always worked better than the regular because, again, for repeated words, you don't want them to keep getting added and added and added to the memory and kind of drowning out the other keys. You kind of want each key to be in there only once-ish. Thanks for the question. All right, so in summary, right, Transformer Excel, we break it into 2 segments, and we're hoping that sort of this history will roll along. Linear attention had really nice scaling, didn't work. Infini-attention is going to basically pack information by using this concept of history. And this history will be available at all the layers. And it's really just a question of how well does this history work. If the history works great, then basically problem solved. And so at least we know that the memory is constant once you've decided how big your memory is. And the compute is linear with context length, which is what we want. You can't get any better than linear. So it's promising. It's interesting. I see people talking about this. And so I'm sure in a few months, we'll know whether or not this is, in fact, what people are using. And there's other things coming out, too. So for references, I have links to the Transformer Excel paper, the fast weight paper, the linear attention paper, and then also wouldn't have been time to cover it, but there's also a very recent paper that just came out a couple weeks ago. And it's this transformer feedback attention memory paper. It's, again, a similar concept where we want to have some kind of recurrent loop that's going to keep this memory of things that we've seen. So we want to have sort of a constant memory access cost. I haven't done a deep read on this paper, but if you find this topic interesting, you might want to check out. This is also from Google, so it's also possible that Gemini is using this transformer fan. All right, so
I have one question. So
yeah.
maybe I missed it, but what size of local attention were they actually using? How did they define the size of their memory?
Yeah, that's a good question. I don't actually remember. So the question is how big was the segment that they were actually using? And I don't really remember, but I'm assuming it's like on the order of like around 1,000. So it's not going to be giant, and it's not going to be 32. It's not going to be tiny.
It seems like if the memory actually works, you would be able to basically say only do a sentence or only do a paragraph or something like that, and then it's just compressing things behind, and then your attention cost goes like much smaller than.
Yeah, so you're saying if the attention worked super perfectly, then why not shrink your window down to something super tiny, like one sentence worth, make it 20 or something like that. Yeah, I don't know. I'm skeptical the memory works that well. Yeah. Also, the way I understand the memory is it's associative. So if you have multiple keys that are similar, you're getting kind of a blend, but you're only getting one. For your query, you're only getting one memory read. Okay. It is possible in regular attention to say, I'm going to put half my attention on black and half of my attention on white. In this, you really can't. You can say that, like, yes, what you're recalling is a blend of great, excellent, good, blah, 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 but you can't also have it pay attention to ball at the same time that it's paying attention to good, great, excellent, right? So I feel like the ability to have that more diverse is why you really, really need that local attention, which local attention is not always just all or nothing, where you attend just to one thing, right? This memory, I feel like it can really only give you one thing per query, and therefore you need to use it more sparingly. But it can help you for that case of I'm reading an entire textbook and something was mentioned in chapter 2 And then it was not mentioned for 10 chapters, but now in chapter 12, I'm going to suddenly start referencing concepts that were in chapter 2. You don't want to be just completely blind to that thing that appeared 10,000, 50,000, 200,000 tokens ago. So this will at least give you some shot at that. But yeah, it can't really like give you, in my opinion, full sentence context from chapter 2. So that's where I think there will still be a gap. But if it can do that well, then maybe most of the time that's good enough. Yeah, it's a good question.
Do you address anything about noisy data? So I imagine that if you're gonna have like this link of data points, and you're doing all these different read operations and everything, and there's this like blending as you described, that you're gonna get some fuzzy memories. And did they like test for the fuzziness or like come up with some more sort of metric like the recall? Like, yeah, I was able to figure out that Bob happened out chapter 2, but like Bob in that instance was misspelled, and but for some reason I was able to like, figure that out or something. Like, was there some sort of measure or like, I guess any sort of means of determining that if that's occurring?
Yeah, so the question was about noisy data. The authors do not specifically address that. That's one of the things that in general happens with LLMs. So if you scrape the internet, there's a lot of really bad text on the internet. There's inaccurate information. There's stuff that's not grammatical. There's stuff that's just kind of slang and informal language or whatever. So I think if you're interested in that, the series of Phi papers, the Phi model from Microsoft. So they're now on, I think Phi 3 just came out in the last month. So they had whatever 1.5, 2, now they're on 3. So they really focus on data curation. So they're like, hey, we're going to use textbook quality text to train this model. And so that's what one of the things that they're really focused on is how much does it help if you don't have noisy data? But when you just train on the pile, yeah, you're getting all sorts of stuff. And so ultimately what you hope is that stuff averages out, stuff cancels out, and that the most important things. And interestingly enough, there is a slight silver lining to it. There are times when I like ask a question of ChatGPT and I make a typo, and it, in my experience, does not care. You know, I swap 2 letters, I miss something or whatever, and it almost always seems to get my intent. So perhaps some of that noisy data actually helps it learn more more robust algorithms, you know, that aren't like dependent on getting perfect data. I have this cookbook, and I thought it was interesting in the whatever preface or whatever they say that not only do they like do recipes that they thought tasted great, but one of their criteria is how idiot proof is this recipe. So they're like, if you have to get the measurement perfect in order for it to come out, then that's not the ideal recipe. The ideal recipe is you do a little too much flour or a little less salt, and it still comes out very close to if you got it exact. And so I think that's one of the things that noisy data may be a blessing and a curse, is that it makes it more idiot proof, but it makes the training a lot harder. Yeah, cool.
That's why I guess I would find it interesting training a model like this, because I agree when if you're trying to model like human intellect or just biological intellect, it seems for whatever reason these systems, when there's a bit of noise introduced, creates more robust systems as you're suggesting. But there's also a tipping point where like too much noise, then it just kind of disturbs the system too much. And so I'm interested for a model like this that seems like they're trying to recreate some level like human memory. Like if they're working with noisy data, what is that robustness? Because if it's super sensitive to noisy data, then this model is just going to be pointless. It's not going to do anything. But if it's also, again, like not sensitive enough, then it's going to be really, you have to be really particular with your queries and stuff, and that's also not helpful.
Yep. I mean, talking about the way human memory works and talking about noisy data, I think empirically we can say that these language models that are just trained on scraped stuff, they work pretty well.
Yeah.
So it would seem like the the ungrammatical and the typos and the incorrect information is the minority that the signal does seem to ultimately dominate. But yeah, there's a lot of things we could talk about. But for this paper, mostly we'll focus on the long scaling. And again, the authors really are not addressing whether or not this memory works like a human or whatever. Really, all they care about is functionally, does it help our language model, regardless of whether it works like anything biological or not or whatever. It's really just about like, hey, can we get access to older tokens in a way that gets good model performance. All right, so I think I'm going to wrap things here because I've already probably taken up well more than my half of the time. I'm going to stop the share for a second, and then I'll bring Ryan up.
All right, I'll try to be quick. We're already a little bit over time, so I'll just power through this. So I'll be talking about the AM-RADIO paper. So this is agglomerative vision foundation model. They're trying to reduce all domains into one. And so the premise of this paper is that we have all of these interesting vision models that can do amazing things, but it's all separate systems. And so the idea here was, can we do something where we combine them all into one? What if we condense them? Is that going to be something even more powerful? Because if you combine the knowledge of all of them, maybe they have some overlap and you can get something extra out of that. And so these huge models, they take a bunch of data, they take a bunch of compute, they can do some really, really cool things. So like there's this segment anything model. So this is from Meta. And so this is a cool little demo of it. You can basically pass anything on it, and then you just like click on a point, and then it'll say like draw the segmentation of that. So you click on a dog, it will give you like the perfect outline of the dog. So like something down here, I can just hover over them, and it's like it just does a perfect segmentation of them, and it can do it for any number of different things. So like I go to the stick, and then it grabs a stick, and so there's a whole bunch of different. Let me move that. Bunch of different models. So that was the segment anything model, and then there's another one, Clip, from OpenAI originally. And basically the idea was give it some text, give it an image, and then find the text that was most similar to that initial image. So like you can have it classify basically anything. So the typical ImageNet model, it's got 1,000 different classes, and it can tell you like dog, cat, bird, but then if you go show it some guacamole, then it doesn't understand what that is because that's not one of its classes maybe. And so on these models, you can pass it in some text as well, and then say like classify it in these 8 different ways or something like that. And so that's a really powerful zero-shot capability. It can understand a whole ton of stuff, and it's able to be trained in an unsupervised way. And there's another model, Dino V2, and that's this model that's been trained to give you a really strong representation. So it doesn't directly do anything for you, but you can kind of use it as your starting point to train for a whole number of different things. So it gives you this vector that's like a really good meaning of what that image is. And so they basically said, here's these three amazing models. How do we condense this into one? Maybe there's value to merging all of them together and we can get something even better. So the trick that they're really pulling at is called knowledge distillation. And so you have these different models. How do I condense this into one? There's kind of this technique that people have figured out where you basically say, I have a whole bunch of data. I have this model that does something. I'm going to pass that data through the teacher model. That teacher model is going to basically label the data in some way. And then I'm going to have a student model that tries to just copy what the teacher is doing. And so that's kind of the premise of this knowledge distillation. And that's fine when you're doing one model, but when you're doing three different models that do completely different things, it becomes complicated because their output isn't the same. And so how do you get them to match the same format and be able to distill information from all of these different things? And so what they did is they figured out that they could kind of add some layers at the end that just map to the various different tasks. So the model, it takes the image and then it outputs an embedding. And then from that embedding, they have some adapter layers that are then mapping to the various different tasks. So you get one mega embedding that can then do all of these different things, which is pretty interesting and powerful. And so they did this at kind of two different levels. So they did one at the summary level, and then they did one at the feature level. So the summary level is just like the regular classification. And then they also, most of these models will output some features depending on like a small local patch or something like that. And so they're training it to mimic both of those. So it's kind of overall decision, and then at the lower level, what it's trying to learn. And the reason that they did that is they wanted it to be like a direct drop-in for all of those different models. So if you could just take one model now and you could say, I can swap this in at exactly the same spot and it's going to give me virtually the same knowledge, that's really powerful because you can swap it into all of the existing infrastructure for those models. And so there's a lot of complication in there. I'll skip over most of it. But to get everything to map together, they had to do a bunch of tricks to get there. So they're trying to merge all of these different representations. So in reality, they have these three different models, and then they had to train adapters for each of those models. So they output some embedding, and then those adapters go to the kind of outcomes of those three different models. And yeah, they want to get a drop-in replacement. And so this diagram on the right side over here is basically showing that you get the input, that's some original data that you have. It's unlabeled, it doesn't have anything associated with it. You pass it through your teacher models. So you can have three different teacher models, and those are going to output some features, and then it's going to output some summaries or classifications or segmentations or something. And then you are trying to get your student model to basically just match those. So this is on the fly, kind of labeling a bunch of data for you in whatever way they were trained for originally. So some of the training details, they did 600,000 training steps, which doesn't really mean anything, but it saw 614 million images, which is a lot, but not colossal. There are data sets that are a billion plus now. So this is a good size, but it's not like record breaking. They use 64 GPUs, and the way that they set that up is half of them were doing the clip and the dyno task at a certain resolution. And then on the other 32, they were doing the segment anything model, because that takes a much bigger input resolution. And so it took a lot more resource. So they kind of had to split them between the groups. And so half of the GPUs are doing that sort of labeling process for clip and dyno, and the other half are doing it for the segment anything model. And then they train this against a whole bunch of different architectures. So these charts over here are basically showing all of the different architectures that they showed and what their throughput was and what their accuracy was. So part of the benefit here is, what if we could take an existing model that took a certain amount of resource to run, and now we can make it 10 times faster or 6 times faster or something like that. And so they figured out that they can distill these existing models and they can make them run
6 times faster with this specific architecture and get similar accuracy by distilling it all away. So this architecture that they came up with, they call e-radio. And there's a whole bunch of details here, but they basically figured out that they can do some blending of convolutional neural networks and a blend of the vision transformers, and they can kind of use that to get benefits from both. So at the beginning layers, they do some strided convolutions, and so right off the bat, it's taking the image and reducing it 4x. So if you had a 1024 by 1024 image and you just downscaled it by 4x, you're losing a ton of information. But because that strided convolution is actually learned, they're able to reduce the resolution, but still keep a whole bunch of information. And so that's kind of that benefit of that initial CNN is it's a learned downscaling instead of just a generic, like, I'm going to take every 4th pixel or something like that. And so that makes it so that the transformer is working on a much smaller resolution, and it's able to be much more efficient. Because like Ted was just talking about with that previous paper, when you have those long sequences, the attention scales really, really badly. And so with this architecture, they did some global attention, they did some local attention, and they put a whole bunch of techniques in there to make them play nicely together. So these are some of the results. So this is kind of, the left side is just a tabular of those graphs that we saw in the previous one. And so you can see the parameter counts, the throughput, and their zero-shot classification, and their segmentation ability, and all of those metrics. And it's kind of interesting to see that we're able to take this, like, this dyno model is huge. It's over 1 billion parameters, and they're able to get similar performance out of something that is a 10th of the size smaller. And so it's not exactly approximating that, but it's pretty close considering you're 10x smaller, and it's 10x smaller, and on top of that, it's able to fit in the knowledge from all of these different models. So it can do dyno, it can do open clip, it can do the segment anything stuff. And then on the right side, what we can see, so the left side is comparing against all of the different architectures, and the right side is comparing against the segment anything model. And so this is kind of the architecture that they kind of figured out was optimal, and they can get this to very similar performance, but actually 121 frames per second instead of 50. So they got a big upgrade on that. I think that's it. Yeah. Any questions? Can you repeat that? Yes. Yeah. So the parameter count is the number of parameters in the model. The throughput, I believe, is frames per second. So how many images they can look at in a second. And then the zero shot is their classification on ImageNet. I'm blanking on this one. I'm not sure on that one, but this is their performance on segmentation. And then I'm not positive on that one either. I'd have to review that.
Was this simply for image classification?
It was trained to do all of the different tasks. So it was trained to do the classification and the segmentation and the general like embedding.
But
Yeah.
all for the task of, so it's doing all the subtasks for the task of image classification. Like it's an all-in-one.
Yeah.
But it's not like, because when you started, it made the ultimate goal is to have something that's similar to like, again, I don't mean the brain, make things analogous to human brain noise, but like, the human brain, we can take audio signals, visual signals, temperature signals, just all these different signals, and then somehow, some way, one system is kind of like compartmentalize and classify and all that. But they're starting small with like specifically image classification, and then like just addressing how to take all the subtasks in one single model.
Yeah.
Okay.
Yeah, so the question was basically this is limited to images. So there's all kinds of different domains, and this is just focused on image tasks. All right, thanks everyone.